This is Science Max, experiments at large. Science Max!
Greetings, Science Maximites. Today, we're gonna be talking about, balance, or what you call balance in science, which is center of gravity. Now, the center of gravity is a place you can find in any object where it's equally balanced on all sides. I balanced this spoon on the eraser of this pencil, and where the spoon is balancing is its center of gravity. But if I take this little tiny dime and put it in the spoon, it doesn't balance anymore. But if I put the dime in this spoon and balance it in a different spot, I can find the new center of gravity, and the spoon balances again. Here's another experiment you can do. Take a potato and a ruler or a stick. Try to balance the potato on the ruler. I'm gonna save us both a lot of time. It's really hard to do. The potato does have a center of gravity, but because of its shape, it's going to be really hard to find and really hard to balance. But if you take some forks and you stick them into the potato, you're no longer just trying to balance the potato, you have to balance the forks and the potato. And it gives it a very different center of gravity, which makes it a little bit easier to find and a little bit easier to balance. Ha-ha!
Whoa! Let's take a closer look at how the center of gravity works. Using our potato. No, that's too close. Back off a little bit. Okay, good. If you want to find where the center of gravity is, you can hang an object and draw a line straight down. Then hang it from a different spot and draw another line. Do this 1 or 2 more times and you can see where the lines meet is the center of gravity. If our potato was balanced on a stick, the center of gravity is a long way from the stick, so it's going to be pretty hard to balance. Now, let's stick some forks in the potato and try again. One line there, a line there, and a line there, and you can see that the lines all come together down here. That's right, the center of gravity doesn't have to be on the object. With the center of gravity way down there, when we try to balance the potato and the forks on the stick, you can see the center of gravity is much closer to the stick. That makes it way easier to balance.
Now, because you're Science Maximites, I'm sure you know that a potato and forks is just the beginning. Everything you have in your house has a center of gravity, which means theoretically, you can balance anything. Try it yourself. Find things around the house and see if you can get them to balance. And if you can't, try adding things to increase the center of gravity and make it a little bit easier. Now we're gonna max it out. That's why I'm gonna go to the center for skills development and training, and we're gonna explore center of gravity even more. See if we can get something to balance. And what better thing to balance than me? Oh, table, right. Hey, this is Sandhya and Swapna. No, Sandhya and Swapna.
Right.
And they are going for their PhDs in science. And you guys, thank you for coming.
Thank you.
Work with Let's Talk Science, right?
That's right.
All about science education, just like us. And I'm glad you guys are here because I need to max out this. Oh, look at it balance. Whoa. Hey, whoa. Okay, I got it, it's fine.
Good. So we're gonna get a gigantic potato?
No, I thought we would use me instead.
So you're the potato?
Yeah, I guess I'm the potato. All right, and I need something to balance on.
Well, how about a tightrope?
Oh yeah, a tightrope. Have either of you done a tightrope before?
Nope.
Me neither. All right, let's set one up.
All right.
Okay, good. Yeah, get some cigarettes.
We're gonna take our balancing potato experiment and max it out. To get a potato to balance is pretty hard, but if you stick forks in the potato, it works a lot better. In our maxed out version, we're gonna balance on a slack line, which is sort of like a tightrope. It's a flat strap tightened between 2 points. And in this version, I'm the potato. And instead of sticking giant forks in me, which is not something I want to try, Sandhya, Swapna, and I are going to experiment to see what I can do to improve my balance.
There. We're using this ratchet strap above a crash mat because we only have it about 3 feet off the ground, but it's still gonna be really hard to balance on, right?
Right.
Okay, so who gets to go first? Okay, here we go. Ready? Hey.
Got it?
No. No. Okay.
I think what you need to do is spread your mass out more to be able to find that center of gravity easier.
So I should balance on one leg?
Start by trying to put your arms out.
Let's
Good
try
call.
this again.
Trying it again. All right.
All right, arms out.
Okay.
Let's see if this works.
Okay, so when I say, you're gonna let go. Ready?
All right.
1, 2, 3, go. No.
It's a little bit better.
It was a little bit better.
A little longer.
That way I went from 1 second to 3 seconds. Yeah.
Yes.
I would like to actually take 1 step.
Okay.
That would be nice.
Well,
What else can we do?
maybe we can try weights. Try and hold them out.
If I have weights in my hands, that would increase the center of gravity in terms of putting
Putting it
the
out.
weight on the outside. You guys have something we can use?
Sure, yeah.
actually.
Okay, good. Wow, these are heavy. Okay.
These are weights.
Yes, they are. Well, that's what they're for. They're supposed to be heavy. Good call. When I hold this one, and I'll borrow your shoulder so I'm, and then when I say, Sandy, pass me the other weight. Here we go. Ready? And pass me the weight. No. Okay, that didn't work. Okay, good. Whoa. Okay, let go. Okay, let go. Oh, no. Oh, it's really hard. I feel I would work better if I could lift the
Yeah.
weights up, but they're too heavy for that.
All right.
So what else can we do?
Well, tightrope walkers use a long pole so that they can balance on a tightrope.
That's right, I've seen that. Do we have a pole?
We
I
can
think
go
we
find
can.
one.
Okay, great. I'll put the weights away. Have you ever heard someone say, I will be back in a jiffy? Well, now you can tell them that's almost impossible. You see, a jiffy is an actual measure of time. It's 1/100th of a second. You see this timer? The first number is seconds. The second number is tenths of a second. And that third number that you can't even read, it's going so fast, that's hundredths of a second. Each one of those is a jiffy. Here are some things that happen in a jiffy. A cheetah moving top speed travels 20 centimeters. A hummingbird flaps its wings almost once. Can you blink in a jiffy? Nope, takes 10 jiffies for that. How about snapping your fingers? 8 jiffies. So the next time someone tells you, I'll be back in a jiffy, you can tell them it took 170 jiffies just to say that.
So I tried walking the slack line, and I wasn't very good at it. Holding my arms out at my sides seemed to help a little. Then I tried holding some weights to see if that would make any difference, and the weights were so heavy, I couldn't really hold them out very far. Now the plan is to try a long pole. Tightrope walkers use long poles to help them balance. The longer the pole is, the more it affects your center of gravity, especially because you can move it up and down to help you stay balanced.
Ta-da!
Nice. So the important thing on this is what? The balance, right?
Yeah, you
That's
want to
right.
find the center of gravity of that as well.
So
you
try
can
and find the center of the
balance
pole.
it.
The center is right there. That's where it balances.
There, you got it.
Okay. How do I
Okay.
hold this and get up on the strap?
I'll help
You're
you.
gonna help me? Okay. Oh. Okay. Uh-huh. Whoa. Whoa.
You good?
Okay. I think I got it.
Okay,
Yeah. Oh,
you're balancing.
check it out. Hey, this isn't so bad.
Hey, look at that.
You can really use it to help correct when you start to fall. You just move the pole, and that's totally helping my center of gravity stay right in the center above the strap. Whoa. Whoa.
You can do it.
A long pole can help tightrope walkers and me balance in 2 ways. First, it lowers my center of gravity. Normally, a person's center of gravity is about here. But with a pole, it changes to way down here, much lower to the thing I'm walking on. But a long pole also helps in another way, because in order to fall off the rope, I have to rotate. It's easier to rotate something that has mass in the middle than it is when the mass is spread out. That's why you put your arms out when you want to balance. A pole works just like your arms. The mass gets spread out way more, and it makes it much harder to rotate around the rope and fall off.
There you go. Center of gravity. We're done. Usually we don't have it figured out this quickly. Usually we struggle a little bit more. All right, high fives.
Way
we did
to
it.
go.
Way
Awesome.
to go. So we did it.
Yeah.
We achieved what we set out to do, balanced with a pole. So how else can we use science to make my balance better?
Well, tops are great because when they're spinning, they balance.
That's right. So the forces used when something spins is something I can use.
Yeah.
All right, this calls for another small experiment. Are you guys good here?
Yeah, sure. We'll keep practicing.
Awesome. All right, back to the lab.
Bye, Phil.
Here's another experiment that's all about balance. Take a pencil and try to balance it on its tip. Doesn't work that well, does it? But if you take a pencil and stick it through a circle of cardboard and try it again, it works. The reason is because this circle is spinning, it creates a force that keeps the pencil standing up. As long as the circle is spinning fast enough, it counteracts the force of gravity because of the conservation of angular momentum. The conservation of angular momentum. The conservation of angular momentum.
Science Max presents Ways to Sound Super Smart. A top will balance when it's spinning. It works because it spins. But why say it that way when you can impress your friends and all the adults you know by saying conservation of angular momentum? Why does a top spin? Because of the conservation of angular momentum. Between you and me, we know that it boils down to the fact that it's spinning. But conservation of angular momentum is how you say it if you're studying physics in university. Just remember to thank Science Max when you impress everyone by telling them a top balances because of, say it with me, the conservation of angular momentum.
Now, let's max this out. Gyroscopic force is pretty amazing. Because this bike tire is spinning, it's hard for me to move it. But it's really hard to see how much it resists a change in orientation unless I do this. Ha ha ha! It looks like it's defying gravity, but really it's because the amount of force needed to change its orientation is more than the force of gravity pulling down on it. It won't last forever, only as long as the bike tire keeps spinning. But you gotta admit, it's pretty cool science. And whoa! Science! Look at that, it totally balances.
Yeah.
So this is a great way to balance. Do you think it'll work if I hold it?
Well, let's see you try.
All right.
right.
So I'm gonna use you to get up on the thing, and then you go give her. Yeah, that's good. And spinning it up. Here we go.
Ready?
Yep.
Okay.
Yeah. Whoa. You can feel it. I can really feel it resisting, and
Yeah.
I think it would work.
I think it just needs to be spinning a lot faster.
That would make it even stronger. Yeah. It kind of hit my chest, so.
You know what? Maybe you should keep it out to one side.
Well, it's still spinning, yeah.
Well, won't that?
I think you need two.
Oh yeah, you're right. One on either side. It'd be great if we could actually have some way I can keep my arms free though.
Yeah.
Oh, I know. Get two wheels and we rope them into some sort of backpack situation.
What?
And we have a way for you guys to get the wheels spinning really fast.
I don't know.
No, I have it all in my head. Trust me. Come on, I'll show you. I'll show you. Wait, you guys go around. Come, don't go on that side of the. Time for a mini-max. Here's how you can use the forces of things spinning around to defy gravity! Well, sort of. Take a ping pong ball and put it in a plastic container like a cup, or this is the top of a CD spindle. put it in and start spinning it around. If you do it right, you can get the ball spinning only on the sides of your container and not touching the bottom. That's centripetal force at work. Oh. It works a lot better and is much more impressive if you have something that doesn't have a bottom. Fortunately, I do. This bucket doesn't have a bottom. Put the ping pong ball in the bucket and spin it around, and if I'm very careful, I can lift the bucket into the air and ta-da! I'm defying the force of gravity. Science! Now I know what you're thinking. You're thinking, Phil, is that it? Is that all you're gonna do? No, of course not. This is Science Max Experiments at Large. This is a garbage can with no bottom in it. And this is a bag of golf balls. Let's see what happens when we put them together. Well, I managed to keep one golf ball in my garbage can. But as you can see, it works really well. And there you go, sort of maxed out. This is a garbage can with the bottom cut out, and this is a soccer ball. I'm gonna see if I can keep the soccer ball inside the garbage can using centripetal force. Okay. It's working! It's very tiring though. How do you throw out a garbage can that's been used? Science!
Here's a fun experiment you can do that plays with the forces created when you spin something. Get a flat platform or a tray and tie rope to every corner. Get an adult to help you with this. Then you get a cup of water. Use a plastic cup, definitely, just in case. You put it on the tray and you start spinning. Now the force is created when you spin something. Centripetal force pulls the water to the outside of the circle. And because the centripetal force is stronger than the force of gravity, no water spills out of the cup, even when it's upside down. If you slow it down very carefully, you'll see that all the water is still in your cup. Now, I definitely suggest you do this experiment outside, and I definitely suggest you do it with an adult. Because when you get tired, which you will, if you don't stop it carefully, you'll have to explain what you've been doing. Science!
Using science to improve my balance has totally worked so far. So now, Sandia, Swapna, and I are trying to figure out how to use the forces created when a wheel spins to help me balance. We need a spinning wheel on one side and one on the other. I've decided to take 2 bikes and remove the handlebars, seats, and front wheels, then cross them over each other and attach them to a backpack. Sandy and Swapna can use the pedals to spin the tires fast, and I will use the gyroscopic force to balance. Or at least, that's the plan.
Behold, the gyroscopic stabilization backpack! Stabilization away! I'm excited. Okay, you think it's gonna work?
I think so. I'm kind of skeptical.
Really? You're skeptical? Why?
I don't know. I don't know if you can do it.
I don't know if I can do it either, but that's why we do science!
Let's see it.
Okay, spin me up. Okay. Oh,
Ready?
yeah.
All right.
And, oh, ready? Go.
Yep.
Oh, yeah. It's working.
Cool.
It's working.
It's actually working.
It's good. Oh, it's getting harder. It's getting harder.
Uh-oh.
Oh, that worked really well until the wheels stopped spinning.
Yeah.
And then what happened?
Well, when the wheel was spinning, it was resisting motion in all directions so that you wouldn't fall.
Yeah, but when they stopped spinning,
You didn't have that anymore.
that doesn't do anything. It's just a 50-pound weight on my back.
Yeah.
Exactly.
Right. So I guess that's why tightrope walkers don't use spinning wheels. They use a pole instead.
Right.
But we've proven that they can.
Exactly.
Yeah. Max said high five.
Yeah.
Woohoo! Yeah! I now have the balance of a ninja circus performer thanks to...
Science!
Thanks for watching Science Max Experiments at Large. Okay, spin me up. Spin me up. And we'll do some more science. Gyroscopic backpack to the rescue. All right, let's go. Greetings, race fans and science maximites. I am Phil McCordick, and this is Science Max Experiments at Large. Today, we're going to be experimenting with the drag racer. Huh? Pretty cool. It works like this. You pull the string and get the wheels going really fast, and then you let it go, and it just drives away on its own. The interesting thing is that I don't have to push it. It goes by itself. It all has to do with Newton's first law of motion, which is an object at rest tends to stay at rest, and an object in motion tends to stay in motion. Yeah. Let's get building. Here is everything you need to build your very own dragster. You need some popsicle sticks, some straws, and some shish kebab skewers. I love these. You can get these at the grocery store. Let's see, some elastics, and of course you want wheels, and I just cut my wheels out of cardboard. So here's a quick explanation of how to build your dragster. First, use anything round to trace 3 circles out on your piece of cardboard. Remember, you want 2 big and 1 small circle. Then, cut out your wheels. Then it's time to make the frame of the dragster using popsicle sticks and elastics. Just put 2 popsicle sticks together, then wrap the elastic band around them to keep them together. First you build one side, then the other side. Then add some pieces across the middle to give it support. Remember not to put any popsicle sticks too near the ends because they'll get in the way of your wheels. Next, cut the straws into small pieces and use an elastic band to tie them to the ends of the popsicle sticks. Then it's just a matter of sticking the shish kebab skewer in a wheel, passing it through the straws, and sticking on the other wheel. Don't forget that the small wheel goes in the middle at the front. You can trim the skewers afterward by just breaking it off short. If you want step-by-step directions on exactly how to do this, you can go to our website. It's all right there. Now the last part is wrap some string around the back axle so you can pull and the wheels will spin. Let's check it out and see how it works. Didn't work that well, did it? That's because we haven't added the secret ingredient. Plasticine, the perfect secret ingredient for all of your dragster needs. And also sculpting, because that's what it's for. Remember how I said an object at rest tends to stay at rest and an object in motion tends to stay in motion? Well, the heavier something is, the more force you need to change its direction, either get it moving or make it stop. That is called inertia. It's the tendency for an object to resist a change in motion, either getting it going or making it stop. So, the heavier we make the wheels of our dragster, the more they will resist a change in motion. So what I've done is I've stretched out my plasticine, and then you roll the wheels of the dragster around in the plasticine, and this will make each wheel way heavier than just the cardboard by itself. And it will make it much better in terms of keeping the dragster going, because if the wheel has more weight, it will have more inertia. Now, I have to wrap the string around the back axle, just like that, and there we go. All right, let's try it out. All right, let's give it a shot and see how it works. Pull on the string, get the wheels going real fast, and there it goes. Now, of course, this is Science Max Experiments at Large, and we are going to do it again, and we're going to do it much, much bigger. That's why I'm going to the Center for Skills Development and Training. I thought it was bigger. Oh, right. Hey, Chris.
Hey, Phil.
How you doing? Chris is from Logix Academy, and he is going to help me max out our dragster. Now, you guys at Logix Academy go into schools and build all kinds of cool stuff with the students, right?
That's absolutely right. This is our dragster over here, actually. And this one has an electric motor, which is kind of fun. And these gears touch.
Ooh.
Wheels get going.
I like that.
And
Oh, all right. See, our dragster works on good old human power. You pull the string, and there it goes. Now, you have a physics degree, right?
I do.
Which means you know Newton's first law of motion.
of course, an object at rest tends to stay at rest.
And an object in motion tends to stay in motion. I thought it was gonna come from over there. Yeah, come on. All right, Chris, I want to make a dragster big enough that we can ride.
Whoa, okay. Well, it's gonna have to be pretty big.
Yeah, I think we have enough wood, though, right?
Yeah,
And
looks like
oh, look, I've got some wheels.
perfect.
These are bike tires, and I filled them full of air, so they're bouncy. Check
Excellent.
it out. Whoa, it's okay.
So, yeah, we build our frame out of wood,
Yeah,
attach the tires on, and then find a way to get them spinning.
and if the tires are spinning,
Yeah.
we don't actually have to push the cart because it'll just go on its own?
That's the idea. The inertia should carry, in the wheels, should carry us down the track.
So in this case, the object in motion is the wheels.
That's right.
And it wants to stay in motion, which means that when it hits the ground, it'll push the cart.
And hopefully us too.
And hopefully us too. All right, let's get building.
Let's do it.
So Chris and I get to work building the dragster. Our maxed out version is gonna look just like the popsicle stick version. A triangular frame with 2 large wheels at the back and a small one at the front. What's more, we're gonna do the same thing to get the wheels spinning. We're gonna attach a rope and give it a pull. When we drop it down, the inertia of the wheels should make the dragster take off.
All right, here we have our dragster. This is nice, Chris.
Yeah, it looks good.
So the only thing I don't understand is what are these for?
Right, so these are gonna help us lift the wheels off the ground, like this.
Oh, okay.
Pull it back, and what's gonna happen is we're gonna run real fast with that string, and we're gonna give it a little kick, and hopefully it'll take off.
Ah, all right, I like it. So I just run backwards as fast as I can.
Fast as you can.
All right, here we go. Ready?
Yep, ready?
Okay, safety glasses on. And, oh, wait, did you want to sit on it, or?
Oh, right. Let's wait until we see it working, and then we can...
Okay, dry run.
Okay, drive it.
Ready?
Go! Run, Phil.
And go! Yeah!
So here's what happened. Remember, the cart has no power of its own. It was able to drive away from a stop using the inertia it got from its spinning wheels, and a little bit from Chris's kick.
That worked pretty well.
That was awesome.
Yeah.
I think we can make it go even better.
You think so?
I just think we need a bit more speed.
Yeah. All right, well, let's pull it back to the start.
Okay.
So what, the wheels weren't going fast enough?
Yeah, I think so. I think that you running, was great, but maybe if we use something motorized.
Well, I think using a motor feels like cheating.
No, not on the wheels. Maybe,
Oh, just to get the wheels spinning fast?
Yes, that's right.
But I don't know how that would work.
Well, I was thinking a power drill.
A power drill.
Yeah.
I don't get it.
Okay.
How do we use a drill?
Let me explain. So we'll take a drill.
Right.
And we'll attach it right under this axle here. And that'll get the wheel spinning a lot faster than we had it before.
Oh, I see. So you put the drill right here at the end, and
That's right.
it'll spin the wheel.
That's right.
Huh.
That's the idea anyway. And once we get it up to speed, hopefully a lot faster than before, give it a kick, it should go a lot farther.
Okay, great. So that's way better than me running all the way back with the rope.
I think so.
All right. Now here's the real question: should we just go for it and have someone ride it when we do it with the drill?
Well, who gets to ride it?
Oh, rock, paper, scissors. Okay.
Let's go.
1, 2, 3. Oh,
Yes.
all right. I will get a drill.
Okay.
What kind of bit do we need?
Hex bit.
Here's a fun experiment you can try. If you have something heavy, like this glass of water, and you put it on a piece of paper, you can experiment with inertia. If you move the paper slowly, the glass moves with the paper, because the friction between the paper and the glass is enough to overcome the inertia of the glass. But if you move the paper quickly, the friction is not enough to overcome the inertia, and the glass stays put. And now, let's max it out. Okay, let's do it. All right, now you might be tempted to try this at home, and you can, but please, for me, promise that you'll let an adult know you're about to do this. And don't use breakable plates. Use plastic plates, because this will take a couple times of practicing before you get it right. Put something on the plastic plates, because the heavier they are, the better it will work. All right. Did I mention not to do this at home unless an adult knows you're doing it? I cannot stress that enough. Okay, deal? All right, deal. Here we go. And there you go. Newton's first law. Thank you.
Our dragster worked pretty well, but now we're gonna try sitting on it and seeing if the inertia of the wheels is enough to accelerate the dragster and the human rider. Because we're gonna need a lot more inertia, we're gonna make the wheels spin even faster using a drill.
All right, power tools! Yeah! Power tools! Woo! Yeah! Sorry.
When I attach the drill to the wheel, it works really well.
Yeah, that is really gonna work. All right, let's do it for real. So, what do you want? Helmet or blast shield?
Blast shield.
Blast shield. All right, there you go. You ready?
Go. There we go. Whoa, man.
Okay.
Remember, the faster the wheels are spinning, the more inertia they will have.
Ready? Ready. And. Well,
What happened?
so you went a foot. 1 foot. So why didn't that work nearly as well as the last time we did it?
Well, I think my extra weight caused a bit of the problem.
Yeah.
So the inertia wasn't able to carry us forward.
But the whole point of this is so that someone can ride the
That's-
dragster. Because why build it if we can't ride it?
That's exactly right. I think if we're gonna have someone ride it, we need heavier wheels.
Well, on the small one we use plasticine.
Yeah.
I don't know if that's what we should use.
What if we used car tires?
Car tires. Oh, what on this?
No, I think we're gonna have to build something bigger.
So so we build a whole new frame.
Yep.
What if we got like the axle of like the back axle of a car or something?
It's a great
The
idea.
back axle of a car, and then what we use the drill
I don't think the drill's gonna be enough.
to move the. Why? You don't think it's gonna be enough to move the back axle of a car?
Yeah, it's too big.
So what do we do?
Well, what's good at moving the back axle of a car?
Well, I mean a car, but we would have to take it off the car. So
We could use another car.
we could use another. We could use another car.
You could use another car.
You'll have to explain how that works.
Okay.
Let's go get the stuff, and you can tell me how we're gonna use. So how do we use another car to make the first car go?
Okay, I'm thinking we jack one car up,
Yeah.
back our big dragster.
Newton's laws in 60 seconds.
Isaac Newton was a super genius, and among the many things he did was come up with 3 laws of motion that describe how everything moves or doesn't move. I will demonstrate using myself. Newton's first law: an object at rest tends to stay at rest. An object in motion tends to stay in motion. Newton's third law is for every action, there is an equal and opposite reaction. These sandbags weigh as much as I do. So when I push them forward, I go backward the same distance. Now, Newton's second law is F equals ma. Force equals mass times acceleration. How hard you push something is equal to its mass or its weight times its acceleration or how much you change its speed. I know, that one's a little bit more complicated, so we're gonna have a whole other segment describing that one coming up. Meantime, let's recap. Newton's first law: object at rest tends to stay at rest, object in motion tends to stay in motion. Newton's third law: for every action there's an equal and opposite reaction. Newton's second: Newton's 3 laws of motion. Now how do I get down? How do I get, oh wait, I know. Oh no, that was not a good idea. That was,
Now it's time for Science So Simple, a caveman could do it. This is a caveman. This is a door. It is a well-known scientific fact that cavemen do not know how to open doors. This is Newton's second law. Force equals mass times acceleration. Our caveman thinks he can open the door if he uses force.
Well, what if he was to walk briskly into the door? Then the force that he will hit the door with will be equal to his mass, or how much he weighs, times his acceleration, which will be walking speed to 0. It didn't work, did it?
No.
Looks like we need more force. If we want to increase the force, we need to increase the mass, increase the acceleration, or both. A rock! That's perfect. If the caveman holds the rock, he has a greater mass. Now we just need to increase the acceleration, which means going faster. Let's try running. Go on. A little further. That's good. Now the caveman is going to run at the door. To get more force, we've increased the mass to a caveman plus a rock. And we've increased the acceleration to go from running speed to 0. And there you have it. That's how Newton's second law works. Join us next time for how doorknobs work.
What?
Our inertia-powered dragster just wasn't maxed out enough. So Chris and I built a second dragster, the Dragster Mark II. This one is a welded metal frame, and instead of bike tires, we're using car tires because they're much heavier than bike tires. And to get the tires spinning fast enough, we're going to use a car. That's right. We jack up an actual car and have the tires touch each other. Then we can get those heavy tires spinning fast enough to get enough inertia to get me going from nothing. The Science Max build team pulled out all the stops on this one.
Just like the smaller version, the dragster has to be up on jacks so the wheels don't touch the ground as they get spun up.
The wheels of the dragster touch the wheels of this working car, which is also jacked up. That's how we're gonna get them spinning fast enough.
Chris is over there. He's got a rope, just like I'm gonna have a rope. And when we're ready, we're going to run forward and pull it off the jacks, and our dragster will go. We hope, right? That's the plan, right?
Yep.
All right.
I think it's gonna work.
I think we should do it. Ready, Chris?
Ready.
You ready, Paul?
Ready.
Fire it up. Go, go, go. Faster, faster, faster. Faster, faster.
Keep going.
All right, Chris. After 3, right? 1, 2, 3, go. Nice. It's pretty good. Yeah, that worked. All right, are we ready for me to be in it?
I think so.
All right, we're gonna do it. The helmet's in the Max van. Do you have the keys for the Max van? Keys for the Max van. Here's another small experiment you can do with inertia. Take a stack of checkers, or game pieces like I have here. Oh, or coins. Coins work really well. And a ruler, or something else that's flat. This is the kind of stick they give you at the hardware store to stir your paint with. Now, you can knock checkers out of the middle of the stack without the stack falling over, if you're very careful. You see, the friction of the checkers leaving the middle of the stack won't be enough to overcome the inertia of the rest of the checkers. Ready? Now, let's max it out. Oh, I have these pizza boxes, and they should work the same way. You see, you get a stack, and don't worry, I've already eaten all the pizza. And I put them on there like that, and now I need a ruler. And what I've got is this cricket bat. You see, it's got a nice flat edge, just like the ruler. Now, if this works right, I can hit it hard enough to knock out just 1 or 2 pizza boxes, and the rest of the stack should stay. Here we go, ready? Science! Awesome. And there you have it, Newton's first law. An object at rest tends to stay at rest, and an object in motion tends to stay in motion. An object in motion tends to stay in motion. Usually there's a sign that kind of...
Well, our inertia-powered dragster worked really well. And now it's time for the final step.
me, riding it to glory.
Now, I know it probably doesn't need saying, but don't try this at home. Not that I think you really can try this at home because this is kind of involved, but I figured I should probably tell you guys just in case you were tempted to try it at home. We know what we're doing. We know what we're doing, right, Chris?
Yes.
Yes, we know what we're doing. All right.
Fire it up. Keep it going. Keep it going. All the way.
Whoa.
All the way. 3, 2, 1, go!
Woo! Yeah! Yeah!
Woo! How's that for inertia?
Wow, look at that. That's amazing.
Cool.
High fives! Yeah!
Let's recap. The weight of the tires, as well as how fast they were going, provided enough inertia to accelerate me and the weight of the dragster. The objects in motion, the wheels, wanted to stay in motion so much they moved the dragster all by themselves. Inertia, and Newton's first law of motion.
Thank you for joining us on Science Max. Let's go again. Your turn?
Yeah, my turn.
Okay. Woo. Greetings, Science Maximites, and welcome to Science Max Experiments at Large. My name is Phil, and today on Science Max Experiments at Large, we're going to be looking at vibration. Vibration is when things go back and forth, and back and forth. All kinds of things vibrate, like pendulums. Pendulums. Wait, and pendulums. Pendulums are designed to swing back and forth. Stop that. Also, metronomes. Metronomes are used by people when they're practicing music to keep accurate time. Yeah. Okay, putting it back. And okay, we're gonna be building. Whoa, okay. We're gonna be building this little guy. This is a vibrobot, and he vibrates and he skitters around on the paper. And if we take the caps off the markers, he makes interesting patterns on the paper. Okay, so let's get started. Let's build a vibrobot. Okay. Oh yeah, you know what? Maybe it's time to take off the ski boots, huh? Whew. There we go, that's better. So today, like I said, we're gonna be making a vibrobot. And here are all the materials you need to make your own. Plastic cup, 3 markers, an electric motor, just make sure you ask an adult first, a battery, a plastic drink bottle cap, a toothpick, scissors. This kind of tape is called electrical tape. Science tape, which is the same as invisible tape, but of course I use this tape only for science. And some modeling clay. And these are 2 bendy straws that I've taped googly eyes to. These are not necessary. I just like them for decoration. Now remember, if I'm going too fast here, which I probably will be, you can get all of the steps on how to make your very own vibrobot on our website. Okay, so here's how you get started. First, you're gonna make the feet for your vibrobot. So I attach some science tape to the markers, and then I put the marker on the bottom of the cup. And then I do that again to the next marker, and then the third, balance it like that. There. Next thing you wanna do is take your plastic drink bottle cap and make a hole with a toothpick. You wanna make it off to the side, right about there. Just like that. That's so when it turns, it will be off center. That's what's gonna give us our vibration. So once you've made that hole, take some modeling clay and stick it in the cap to give it some weight. When you've done that, stick it onto the shaft of your motor like this. See how it's off center there? Now we just need to attach it to the vibrobot. I just put it right here on the top, and I like to attach the battery to the back of the cup. And now, finally, we're going to attach the eyes. We take some science tape, and we put the straws over here. I am vibrobot. I am here to vibrate. Take me to your leader. So then, you attach your tape with the wire to the top of the battery there, and then the other wire to the bottom of the battery, just like that, and let your vibrobot make some art. Ha 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 ha. Now, if the battery is new, your vibrobot might be jumping up and down quite a bit. So you can do what I like to do and add some more weight, and then you make better lines with your vibrobot. And your vibrobot makes art. How long will he last? Probably till lunch. And there you go, vibrobot art. Art made by a robot. How cool is that? So that's what we're gonna do today. I'm gonna meet Chris from Logix Academy, and he's gonna help me max out the vibrobot. Plus, we're gonna learn a little bit more about vibration. Come on. Oh, hey, Chris.
Oh, hey, Phil.
Thanks for coming.
My pleasure.
Okay, here's your Science Max lab coat.
Thank you.
So you guys at Logix Academy, you also build a vibrobot, right?
That's right, we do.
This is mine, and it works pretty well.
That's awesome.
So, I want to max this out.
Cool.
So I thought we would start with, instead of this motor, we would start with this motor.
Wow.
It used to be a round circle, but I cut it off so that it's off-center.
Perfect.
I've also got, this is our battery.
Fantastic.
That's as far as I've gotten so far.
Well, it looks like we need a frame next.
Right, something to be the cup.
That's right.
So we just need some sort of larger cup.
Ooh, how about that metal shelf over there?
Oh, this thing?
Yeah.
This is just something I keep my parts on.
It's perfect.
Really?
Yep, the shelves will house everything that we need, and it looks like it'll be strong enough to hold everything together.
Now, the vibrobot had markers on the bottom of it.
That's right.
To make a little pattern. Should we try that with this?
Because we're going bigger, what if we use paint and paintbrushes instead?
Okay, sure. We could attach paintbrushes to the legs. Pass me one. All right, so now all we need to do is get some paint and some paper.
That's right.
And we can fire it up. Okay, let's move it over this way.
Vibration and frequency. What's the difference? They're all connected. Ta-da! Now we get, whoa. Vibration is things going back and forth. Back and forth. And back and forth. It's a cycle. Cycle, 25 bucks. Oh yeah, it's the wrong kind of cycle. Never mind. Well, if that's vibration, then what's frequency? Well, frequency is a measure of how fast or slow, how frequent those vibrations happen. Look at this bowling ball. Look. It is swinging back and forth, but not very fast. You could say it has a low frequency. We measure all kinds of things by their frequency. This thing is terrifying. When you turn the dial on your radio, you're tuning in to different frequencies of radio waves. Hey, look at this punching balloon. It's going very fast. You could say it has a high frequency. So, now you know. Vibration is something going back and forth, and frequency is how quickly it does it. Ramona, the bowling ball keeps coming through everything. How do you turn it off?
Okay, back to our main experiment. Chris and I are taking a vibrobot and maxing it out. We have a large motor and a battery, and we're taping it all to some shelving. Just like our small vibrobot, our motor needs something to make it unbalanced when it spins. That's what will cause the vibrations.
It's just taped. I haven't attached it in any other way. Do you think that's okay?
As an engineer, I have superior faith in duct tape.
Okay, well, that's good to know.
We're also adding an on-off switch and some paintbrushes on the bottoms of the legs so our maxed out vibrobot can make art just like the small one. The final step, dipping the brushes in paint and setting it on a big piece of paper. We fire it up and it immediately shakes everything off the shelves.
It totally spilled all the stuff on the shelves.
The motor shakes the vibrobot a lot. But there's a problem. All that shaking is starting to take its toll on the shelves. The wheels come off, the screws come out, and finally...
Whoa. It totally shook itself apart.
Destroyed itself.
The shelving unit just completely falls apart when it's being shaken.
Vibration is really hard on the structure of an object. We need something more sturdy, something that can take weight.
Steps, maybe?
Yeah.
Okay, hold on.
Okay.
Okay,
Yeah, this looks much better.
Okay, great. So we build the new vibrobot out of this. So more paintbrushes,
Bigger motor, more paint,
more everything.
more everything.
All right, good. This is a pendulum. It's just a weight suspended on a line and anchored from above. Pretty simple. Pendulums were used for hundreds of years for all kinds of reasons, but most famously in clocks. Why were pendulums used in clocks? Well, here's why. Let's mark every time the pendulum hits the bottom of the swing, right here. Okay, watch. All right, now here's the question. How fast will the beeps be if I swing it from much higher up? Let's find out.
No matter how high the pendulum swings, it keeps the same frequency. That's why they were used in clocks, because it could swing for a long while, and even though it would lose energy, it would still keep perfect time. The frequency of a pendulum doesn't change, no matter how high it swings or how much weight is on the bottom. The frequency comes from how long the line is.
Now this is a pendulum wave.
Because each bowling ball has a line that's a different length, they have a slightly different frequency. They start out swinging together, but soon they start to make interesting patterns. Remember, each pendulum is keeping its own perfect time, even if it's slowing down. It's only the length of the line that gives each pendulum a different frequency.
And now we're gonna max it out with well, I guess these are already bowling balls, so this is already pretty maxed out. I'm just gonna leave that there. These are balloons. This is a laser, and these are awesome laser safety glasses. Now, lasers are made of light, and light has a frequency. In fact, each color of light has a different frequency. This is a red laser. Check it out. Yeah, cool. This is also a very powerful laser. Oh, I can pop the blue balloon with the red laser because the blue absorbed the red light from the laser and then it heated up and the balloon popped. But here's the cool thing. I cannot pop a red balloon with a red laser because the red balloon reflects the red light from the red laser and I can't pop it. If I wanted to pop a balloon with a red laser, I need to use a darker balloon, one that absorbs the red light, like a black balloon. So there you go. Lasers, frequencies of light. I'm gonna keep this red balloon because it's always nice to have a balloon.
Chris and I are maxing out the vibrobot, but our last version shook itself apart. Now the plan is to start with something more solid and try again. We found some very solid steps and added an even bigger motor, an even bigger battery, and attached a half-circle wheel to make the vibrations when the motor spins. We add some paintbrushes and fire it up.
Here we go! Come on!
Go, vibrobot!
It wants to move.
Is it moving at all? So it's still not working. It's sort of getting caught in the paper and it's on the paintbrushes.
And the paintbrushes seem to be absorbing too much vibration, and then the paper's stopping it as well.
So why don't we remove the paintbrushes?
Yeah.
And we might as well remove the paper if we don't have any more paintbrushes.
Yes.
And we'll see what happens.
We'll see what happens.
Okay. No paintbrushes, no paper.
Okay.
Now let's try it. 3, 2, 1, go!
Yeah! Aha! It's moving. Not bad.
The shaking is good, but I don't know if the shaking is enough. So what do we do?
Well, we could add another battery.
Another battery which would give it more power?
That's right.
Okay, let's try that.
Okay.
Okay, so it wasn't working before.
No.
Not enough power. And now we've got a second battery here.
That's right. We've wired them up so that one power feeds into the other, so we've got twice as much juice as we did.
So it's just a matter of clipping this onto there.
That's right, but hold on.
Yeah, safety glasses, because now we don't know what's going to happen anymore. Ready? 3, 2, 1.
The extra battery makes a big difference. The new vibrobot shakes around and only shakes itself apart a little.
All right, that was was amazing. Okay, so all we needed was more power.
That's right. I think it didn't have enough power to vibrate up and down, and that's why it wasn't moving every time it hit the ground.
So I think if we're gonna use this much power, I think we need to build it again.
Okay.
Build it even stronger and with a bigger motor.
Yeah?
And more power. And then maybe I ride it. You think we can build that?
Of course.
Of course. Okay, let's do it. You want to see something cool? I can make this water levitate, defy gravity using the power of science. You want to see? Behold! Gravity-defying water. I can even make the water go very slowly. Or I can make the water go back up into the hose. Or I can make the water completely stop. You know what's interesting? The water does not seem to be stopped for me. You see stopped water because you are looking at it through a TV camera. See? Real life, TV camera. Real life, TV camera. You see, movie cameras and TV cameras take a whole bunch of still photos and then run them together really, really fast. 24 times a second for our TV cameras. I have created a device that drops water at 24 times a second, and what happens is everything lines up. So it looks like the water drops aren't moving. But watch this. I grab the hose and it's fine. But I let it go, and the hose is vibrating back and forth at exactly the same time the camera shutter is going back and forth, and everything looks like it stopped. The power of frequency has defied gravity. Okay, so not really. It's kind of a camera trick, but I prefer to call it science.
Here's a fun way to play with things going back and forth. This is Euler's disc, and it's designed to spin like this. What's going on is friction and gravity are slowing that down and pulling it towards the Earth. Now, you don't need a fancy disc like this to do this at home. All you need is a pot lid. Check it out.
When the pot lid spins, friction and gravity start to slow it down, which means each spin gets lower and lower, and the frequency gets higher and higher. But the difference between a pot lid and Euler's disc is Euler's disc is made to go for as long as possible. The heavy puck has a slightly rounded edge and sits on a glass surface that is slightly concave, like a bowl. All of this is designed to make Euler's disc last a really long time.
Which is quite a while.
But eventually, friction and gravity pull the disc down, and finally, it stops.
Pretty amazing, right? Well, wait till we max it out.
This is Trevor, head of the Science Max build team.
Hey.
Thanks for setting this up, Trevor. So what is this?
This is a giant side of a spool, big hydro spool.
Okay, so this is the largest disc that we could totally find, and we've got it all hooked up here. We lift it up, we spin it, and then you pull the thing and it will drop down and spin like a coin, because it's the only way we can do that with something this heavy.
Yeah.
Ready?
I'm ready.
Okay.
Trevor and I hoist it up and get it suspended above the ground. Then I start to wind it up.
Ready?
When it's going fast enough,
And go, Trevor!
Trevor pulls the release and it turns out a 200-kilogram spinning disc works exactly the same. As it spins and rolls, gravity and friction work on it, and the frequency speeds up as it gets closer to the ground until it stops.
Giant Euler's disc. Nicely done, Trevor.
That was awesome.
That was great. Let's do it again.
All right.
Our vibrobot was working well, so that means it's time to make it way bigger. We started with a big metal table and added a huge motor, one 20 times as powerful as the last one. Instead of batteries giving us 12 volts of power, we're going to use a plug, which is 10 times more power. We've added an off-center wheel for vibration, bolted the motor to the frame, and added a protective cage all around to prevent anything from flying off. It even has a seat for me to ride.
Okay.
Okay?
You ready?
Ready?
Here we go.
We fire it up and it's very shaky. Oh, wow. Wow. That was really uncomfortable. It was like very bangy, even with the seat.
Yeah?
I'm gonna try standing on it.
All right.
When I try standing on it, the vibrobot lives up to its name. It vibrates all around the lab. Oh, wow. My legs are numb to the knee.
I'm not surprised.
Vibrobot!
All right.
Yeah, that worked really well.
That was awesome.
I really can't feel my feet right now. And it held together, which is impressive.
That's right. The more power and the stronger structure paid off.
Yeah, the only thing I regret is not getting a chance to, wait a minute, come with me. Okay, so I achieved my dream of riding the vibrobot.
You did.
But we never got a chance to make art, so we've dipped a whole bunch of nuts and bolts and heavy things in paint.
Yep.
And now we're gonna turn on the vibrobot and see if we can make some art. Let's see how it looks.
Oh, wow.
Ta-da! Vibrobot art. Vibrobot has been a huge success, and we got some art to keep. High fives. Well done. Science Max, experiments at large. Who gets to keep the art?
Rock, paper, scissors.
Okay. 1, 2, 3. Okay, tie. 1, 2, 3. Tie. 1, 2, 3. 1, 2, 3. Wow. 1, 2, 3. Ah, tie. 1, 2, 3. Man! Greetings, Science Maximites. Today, we're going to be looking at air. I know, it's kind of hard to look at air because it's invisible. But we can look at something that uses air to move. That's right, paper airplanes! Ha-ha! Ho-ho! Look out! Woohoo! Believe it or not, you can learn all kinds of science from paper airplanes. So let's build some. We are going to do a paper airplane, which actually holds the Guinness World Record for the longest paper airplane flight. Pretty cool, huh? First, you fold the paper in half like this, but then you open it back up again, and then you fold in the corners like this. Now, don't worry if this is really, really fast, because you have all the instructions on our website. Then you can fold the paper down like this, make sure it's about 2 centimeters from the bottom, where the point is there, and then you fold the corners in just like you did before. But these ones are just guide folds. We use guide folds to help us fold other folds, basically. Now, we fold again using the guide fold lines you just made. And I like to call this fold the shirt collar fold because it sort of looks like a shirt collar when you fold it. Now, we fold again on the fold that you made before. Folds in like that, and in like that. And now we fold the point down to touch the edges right like that. And this is a guide fold, so do it very strong. Unfold it. Now you fold it in half like this. And see that guide fold line that we made there? What you're gonna do is you're gonna take the tip and you're gonna fold it in to touch the guide fold line like that. And this is also a guide. And open it up. And here's the trickiest part. See how it's bent like that? Push it open like this, and this is called a pocket fold because you want to make a little pocket and push it up against there. Fold it flat like this, fold this tip down over there like that, then fold it around the back side, then fold the wings down like this and like this. And here's the extra special bit. We're gonna use some stabilizers on this plane. Fold up the stabilizers on the ends of the wings, and ta-da, the Sky King paper airplane fold. Now, as Science Maximites, you know that there's lots of ways you can learn how to fold paper airplanes. Get an adult and look up paper airplane designs on the internet, or take a book out of the library on how to fold paper airplanes. And of course, this isn't Science Max, experiments at large, if we don't max it out. So that's right, we're gonna make a giant paper airplane. I'm going to the Ontario Science Centre to do just that. That's never good.
Whoa, Phil, I'm so sorry. You okay?
Yeah, I'm okay, Justin. I never know where the portal's gonna spit me out. This is the Science Center, right?
Well, that's right. In fact, you've landed in our paper airplane laboratory.
This is what happens to me, Justin. I make a paper airplane, I fold it perfectly, but then it flies like that, or it does that, and I don't know how to fix it.
Okay, well, that will happen. But you know what? There are really only 3 ways your paper airplane can fly, and I can teach you how to control each and every one of them.
Great, let's do it.
Let's do it.
All right.
Science Max presents how to fly your paper airplane. Is your paper airplane spinning around and around? Well, that's what you call roll, chum. Roll is what you call it when any plane moves like this or like this. Here's how to fix it. Bend up the back of one wing to create more lift on one side, and it'll balance out. Happy days.
Okay, so let me try mine.
What's that? Your airplane goes straight up or straight down? Sounds like you have a problem with pitch. Sorry, pitch. Pitch is when your airplane moves like this or like this. To fix it, bend the ends of both wings up if you pitch down, or down if you pitch up. Adding a weight to the nose also helps if you've got a problem with high pitch. High pitch.
Great, your turn.
All right, here we go.
Is your plane turning this way or that way? Yeah. Yeah? No. Yeah. Yeah is when your plane moves like this or like this. To fix it, bend the back of the plane like the rudder of a boat.
Okay, great. Let me try mine. Not bad. You try yours.
Here we go.
Oh, yeah.
That was pretty cool.
That's what we want.
Yeah.
You know what? Are you ready to build a giant paper airplane?
I think I am.
Fantastic. I just need to get one more expert. I will be right back.
Cool.
Hey, David, how you doing?
Hey, good.
Good. So David's going for his Masters of Applied Science.
In aerospace, science, and engineering.
So you know all about planes.
I do.
Great.
Yeah.
So what does this have to do with planes? What is this?
So this is a water channel, and it allows us to test airplanes in it before we put them in the sky.
Great. We'll have my airplane, and we'll just put it in here, and we'll test it.
Please, it's made of paper.
Yeah?
And in the water, it becomes soggy.
Well, how do we test our paper airplane if we can't put it in the water?
Well, this is a classic airfoil shape.
Yes. Now, is that what you call it, airfoil?
An airfoil, yeah. So the cross-sectional shape of a wing is called an airfoil.
Okay.
And that's what generates the lift. Fortunately, air and water are both fluids, so they behave in the same way. I could push ink into the water, and that's going to allow us to see how the fluid flows over the aircraft. So if you tilt its nose up a little bit, you'll be able to see that the shape of the airfoil is actually pushing the water downwards.
Oh, yeah, you're right. The ink doesn't go straight. It follows the wing down.
It follows the shape of the wing down, and we have a lower pressure on the top of the wing and a higher pressure on the bottom of the wing, which pushes it upwards.
Right,
generating
and
lift.
that creates lift.
Exactly.
So you guys use this all the time in aerospace?
Yeah, yeah.
That's pretty
Absolutely.
neat. So, are you ready to design an even bigger plane, a giant paper plane?
I'm confident we can do a good job.
I am excited about it. Let's do it right now. The big paper's over this way. This way. Okay.
Here's the plan. Take a giant piece of paper and fold the exact same airplane we did in the lab. The small one flew. The large one should too, right? Well, let's find out.
I believe we are ready to make our giant paper airplane. All we need is a giant piece of paper! Okay, be very careful getting off it. Whoa! All right, let's fold it. Nose on that side. Okay.
Remember, we're folding the exact fold we did in the lab, only on a larger scale.
We have a tape malfunction down here.
But it's a lot harder to do with a giant piece of paper.
Fantastic. That's pretty good.
Okay. There.
Perfect.
Yeah. Giant paper airplane!
This doesn't look too much like an airplane.
No, it's way too floppy.
Yeah, but I mean, maybe it just needs, like, when I throw it, maybe it'll catch the winds, and then the wings will come up like that.
Whoa. Yep. Maybe.
Like, I'll just.
Give it a try, Phil.
Okay, I'm gonna give it a try. Giving it a try. Okay, you guys ready?
Yeah.
Go for it.
Here we go.
Oh man.
I think we can make some improvements.
It sort of felt like a bed sheet. I feel if I just threw my lab coat, it'd probably look, let me just see. Okay, ready? Yeah, it looks pretty much the same, doesn't it?
Yeah.
So, I didn't know this, but when you fold paper that big, it sort of behaves like fabric.
Yeah, very, very floppy.
Very floppy. What if we supported the plane, like we put struts or something in it, like this stick? If we put it on the wings, it'll stop it from being so floppy.
Right, and you can tape it on.
Yeah.
That's a great idea.
Yeah.
We need bigger sticks.
Yeah.
Really lightweight.
Like foam.
Yeah,
Stuff?
and like hollow tubes.
Hollow tubes.
Good.
Good. So we'll put a whole bunch on there. We'll tape them on so that it doesn't flop around.
Yeah.
We'll try to get it.
Yeah.
Yeah, I think we got something.
Okay, great. Let's go.
All right.
Bernoulli's theorem states that faster moving air has lower pressure than slower moving air. You can demonstrate this yourself with a ping pong ball and a hairdryer. You put the ping pong ball on the stream of air from the hairdryer, and because it's moving quickly, it has lower pressure than the air around it. So the low pressure air works sort of like a force field, and you can defy gravity with your floating ping pong ball. Awesome! But of course, this is Science Max Experiments at Large, so we have to max it out with a giant hairdryer and a giant ping pong ball. Sorry, I said science! You probably couldn't hear me because of the... So, our giant paper airplane turned out to be really floppy. When paper is that large, it doesn't hold together very well. What we're going to do is take foam and long sticks and tape it to the large paper airplane wherever we need to give it support. So, here, and here, here, and a bunch there, and maybe some over there. Well, it turned out we needed to reinforce in a lot of places.
There. And then that.
Great, look at that. It's not even flopping around. It stands under its own weight. Huh?
There's a whole bunch of stuff on it. I don't know if it's gonna fly so well.
Oh, it's gonna be, well, I mean, I have to put the stuff on it so it doesn't flop around.
But there's like really a lot of stuff.
Well, I needed this foam to reinforce this foam, and then I needed the cardboard to reinforce both of those.
Phil, there's a giant hole in the wing.
Well, I can fix that. Just move your head, and then I'll just...
Phil, there's a lot of stuff on here.
There.
But like it's really a lot.
Problem solved.
Guys, let's just fly it.
Oh, okay, sure, yeah, let's do it. Let's do it. All right.
Okay. All right, here we go.
Maiden voyage of the Mark II giant paper airplane. Okay, here we go. 1, 2, 3. So it went about 3 feet. So that didn't work.
I told you, too much stuff.
You did. He told me that.
He said that.
He said that.
What we need is something that's stiffer without as much stuff on it.
But the paper, it's too floppy, so you have to put the stuff on.
Right.
How about some cardboard? Cardboard's nice and stiff, and technically it's paper.
You're right, cardboard. Let's make it out of cardboard.
Yeah.
Cardboard, all right. Oh, yeah, it's over here. Tornadoes are giant weather systems that cause the air to go around and around. Tornadoes can be pretty dangerous, but they don't happen that often. Here's how you can make your own small pet tornado you can play with at home. Because air and water behave similarly, we can make a water tornado. You spin it around, get it going, and ta-da, your very own pet tornado. Here's how you do it. You take two 2-liter plastic bottles and fill one with water and some blue food coloring, is what I like to do. And then tape the mouths of the bottles together. You might need an adult to help you with this because you want to make sure the bottles are perfectly aligned. Then flip it over, spin it around to get it going, and voila, your very own pet tornado. Awesome. And now we're gonna max it out with a giant tornado chamber. Michaela.
Hey, Phil.
So this is your giant tornado. It's amazing.
Yeah.
So I made one with plastic bottles and water, but this one uses air, just like real tornadoes do in the wild.
That's right.
So how does this work?
Well, here we have a platform, but underneath that there's a fog machine that's pushing the fog up. And we've created an updraft because there's a fan at the top that's pushing air out of the top. And also we're trying to mimic the intense winds you'd get from a tornado with these pillars that are shooting out air in this direction.
So it goes around in a circle.
Yeah, in real life, tornadoes are pretty rare. You need a perfect set of conditions to see them. You need warm, humid air and cold, dry air. And as well, some intense winds that you usually get from thunderstorms.
Science! If I was to drop this light basketball and this heavy workout ball at the same time, which do you think will hit the ground first? Let's find out. They landed at the same time. That's because everything falls at the same rate. It doesn't matter how heavy or how light something is. Until things are falling fast enough that air friction or drag starts to play a factor. Soon, things reach their top speed. This top speed is called terminal velocity. It means I could throw this basketball from an airplane and it might not be going any faster than if I threw it from, say, 10 stories up. I'm gonna find out what the terminal velocity is for both of these objects when we max this out. Ninja science roll!
Here's how terminal velocity works. Everything falls at the same rate, going faster as gravity pulls it down. But when things start going so fast that just pushing through the air at that speed creates as much force as the pull of gravity, things reach a top speed and they won't go any faster. How heavy something is and how much air it pushes both play a factor in its top speed. And that top speed is called terminal velocity.
How cool is that? I'm at iFly Toronto. This is a giant wind tunnel, and they've got the wind going fast enough that they can't fall any faster. It's the terminal velocity for a human being. I'm gonna take our weighted ball and our basketball and place them both here in the wind chamber. This is the control panel, which is what they use to control the wind speed inside the chamber. And this is Derek, who's gonna be operating it. And that is Mike and Greg, and they're inside the chamber. All right, let's fire it up.
All right, firing it up.
35, 58, nothing happening yet. This number here is the one we're looking at to see how fast the air is moving. 86, something's starting to happen. Oh, 89, wind speed of basketball, 89 kilometers an hour.
At 89 kilometers per hour, the wind is going fast enough that the friction of the wind and the pull of gravity balance out, making the basketball float. This means you could throw a basketball out of an airplane and it would never go any faster than 89 kilometers per hour.
All right, let's keep increasing the speed. 106, 124 kilometers an hour, 140, 150. Oh, 166, almost. 172, whoa. Wind speed of the heavy red ball, 173 kilometers an hour.
Because the red ball is heavier than the basketball, we need a lot more wind speed to counteract the force of gravity before they cancel out and the ball floats. Here's something else that's going on that's cool. Mike is flying, but Greg is not. That's because Mike is lying down, which means he's catching a lot more wind than Greg is, who's standing straight. If Mike stays lying down, his terminal velocity is the same as the red ball, 173 kilometers per hour. But Greg's velocity would have to be a lot faster.
And that's science!
So the giant paper airplane hasn't been working so well. The problem is paper can't hold up its own weight when it's that large. Cardboard is much stronger than paper, so we've decided to rebuild the plane out of cardboard.
All right, Phil, hoist it up.
Then we take it to the roof of the Science Center and see if we can get it to fly.
Oh, woo! There you go, our Mark III model paper airplane. Now, I know it's made out of cardboard, but cardboard is technically paper, and it's the only thing strong enough to hold a plane of this size together. We even had to put some poles in so the wings still wouldn't flap. But we're pretty confident this is gonna work. Okay.
All right, Phil, we're in position.
Now, don't try this at home. Our roof has a big wall on the edge. Your roof does not. Our first attempt didn't go so well. Looks like we have a bit too much pitch. Our second attempt still had a bit too much pitch. Time to add some weight to the nose.
We added some clips to the front to give it a little bit more weight on the nose, which is important. Although at this point, I kind of wish there was less weight. Whoa, okay, all right.
Phil, that was great!
All right!
This throw worked best, but I know what you're thinking. Why didn't it sail through the air like a normal paper airplane does? Well, that's because the other thing heavy planes need to fly is thrust. So we could put an engine on our plane, but then we'd have to use something stronger than cardboard, and well, pretty soon we'd have an actual plane. But this isn't about making a full-size plane. This is
Largest paper airplane I've ever thrown! Woo! You guys are great! The plane is great! Thank you very much for watching Science Max Experiments at Large. Where were the stairs? Yeah. Oh, never mind, I found them. Hey, Science Maximites, slippery. But that's okay, because today we're talking about friction. Friction is a force that is everywhere and happens when any one thing rubs against any other thing. We do lots of things to increase friction, like wear shoes with big treads on them. And we can do things to reduce friction, like the experiment we're doing today. We're gonna build a hover disc, and it's very easy. You take some cardboard and cut it into a circle, just like this. Then put a hole in the middle of the circle. You might want an adult to help you with that. And then take a plastic drink bottle cap, like this. I like to use the ones that you get on sport bottles because they have a little nozzle that pops open or closed. And then you glue it around the circle, and you get this. Then you need a balloon. So you blow up your balloon. I know you know that step. And then twist the balloon so it doesn't get away from you. When it's nice and twisted, you can stick it over the drink bottle cap like this, and then untwist it. And this is why I like to use the plastic drink bottle caps that come from sport bottles, because you can open it when you want. And when you do, your disc rides on a cushion of air, reducing the friction with the table, and it's almost like it's sliding on ice. You can also use CDs if you want to do a different design. Just make sure you're using CDs you never want to listen to again. Now, if any of this is too fast, don't worry. You can always go to the Science Max website, where we have all of the instructions. And now, it's time to max it out. We're going to see if we can make a human-sized, rideable, low-friction hover disc. I'm going to the Ontario Science Centre, where hopefully I have an expert that can help me. Door is stuck. I think there's a little bit too much friction with it. Oh, that's got it.
Oh no, this isn't the Science Center. Did I go back in time again?
Oh. It is the Science Center. Helena, hi.
Hey, Phil. You're here to see the hover disc.
Yes, please.
All right, come on, right this way.
So I made one in the lab that works pretty great. It's on cardboard and it has a balloon. The one you have here works on the same principle?
Yeah, it does. But you know what? My friend Russell has some ideas about making something like this, but even bigger.
Do you think we can make one big enough to ride?
Maybe, yeah.
All right, well, let's take a look at the one you have here. Oh, I see. Right, this one works the same as the one I made. It's really hard to move the disc, but if you add some air, it floats like a dream.
There we go.
Great, so let's ride it.
Whoa, Phil, not this one, the one upstairs. You can ride that one.
Oh, okay.
Yeah.
Should we bring this one just in case?
No, it's a little heavy. I think we can leave it there.
What if we need it for reference?
No, I'm sure we'll be okay.
It is pretty heavy.
Yeah,
but...
come on. Let's go. Russell's waiting.
Are you sure we won't need it?
I'm positive.
Okay, but if we have to come back, I get to say I told you so.
Okay.
All right.
Hey, Ramona, you change your hair? Yeah, it's nice. It's like doing this now. Because but now it's, yeah, I like it. You should give me the name of your guy, because I wanted to, hey, oh, hey, how are you? You ever think to yourself, no matter what I do, I can't seem to get anywhere. I can't get enough traction? Well, you, my friend, need some more friction. Which one of these two shoes has more friction? Take a closer look. Huh? Right, bam. This one doesn't have a lot of treads. It doesn't have a lot of friction. But this one, it's got metal spikes on the bottom. This is called a cleat, and the spikes are for helping you grip onto the grass when you're playing soccer or golf, increasing its friction. Why do you think skis are smooth on the bottom? Come on, look at that. It's so smooth and glidey. My hand I can barely even touch the surface. It just slides right off. It's sort of glidey and smooth. They're smooth to help you glide across the snow, reducing their friction. Why doesn't this box slide down this ramp? Friction. This roller skate has wheels. Wheels reduce friction. But when I push the roller skate, how come it doesn't just keep rolling forever and ever and ever and ever? And going all the way around the world and writing a memoir. Say it with me. Friction. Louder. Friction. Can't hear you. Friction. A little too loud. Friction. Ease it back. Friction. How can I hang onto this rope without falling? Friction. How can I jump down on the floor without falling over? Friction. And now you know your friction. Your friction. Your friction. Come on. Uh-oh. Oh, Ramona, the friction sign is broken. Reset. Uh-oh.
The plan is to take our small hover disc and make one big enough to ride. So I'm off with Helena to another part of the Science Center to meet Russell, who has some ideas on how we can do it.
Oh, hey, Russell.
Hey, hi, Helena. Hey, Phil. How you doing, Russell?
How you doing, Phil?
So this is the hover disc.
This is our small hover disc, yes.
How does it work?
Well, obviously you sit on here,
right.
Air will go into here. It gets vented through all these separate holes here, so we get an airflow over the entire area. Hopefully this will work to pick someone up. All we need is...
air.
Oh, well, that's easy, because the small one worked like this, so we just put the balloon on, right?
I hope you got the
Okay, so we put the balloon on the... hold on. Larger balloon!
Oh, okay.
Sorry.
That's okay.
Okay. Yeah. Uh-oh, twist it so it doesn't...
He's losing his air!
Okay.
All right. On you get. You grab
Right.
one side, I'll grab the other.
Okay, here we go.
Go.
It doesn't
feel way too much
It doesn't
friction
feel
on
like
No.
it still feels pretty frictiony. I think we might need something more than a balloon. So what do we do?
Well, I think we need more consistent air going through here.
Okay. So not a balloon.
Not a balloon. Something, I don't know, opposite to a vacuum cleaner?
Opposite to a vacuum cleaner. That would be
Like a leaf blower.
Like a leaf blower.
a leaf
yes.
blower.
Right?
High five.
Yeah.
Awesome idea.
Yeah, leaf
so
blower it is.
why don't we make a couple larger discs, and we'll hook some leaf blowers to them, and we'll see what happens.
Definitely give it a go.
Okay, great. Carbon is an atom and is the basic building block of all life as we know it. You, me, all plants, all animals are carbon-based life forms. Other things are made of carbon too. Diamonds are carbon, coal is carbon, even pencil lead isn't lead, it's graphite, which is carbon. If you were to take all the carbon atoms in your body, you could fill 9,000 pencils. Of course, kind of prefer my carbon where it is.
Our low-friction hover disc still had way too much friction. One of the problems that Russell mentioned is that the balloon just wasn't giving enough air. But then, Helena had the idea of using a leaf blower instead. The plan now is to make a leaf blower-powered disc by starting with a big circle of wood, cutting a hole in the wood where the air will come through, and then covering the bottom with a tarp that has many holes cut out of it for the air to escape. Because leaf blowers are made to push lots of air, hopefully there'll be enough for me to ride it.
Well, this is the business. Look at this.
That's amazing.
It's good, right?
Oh, yeah, I love the tube. You know, high volume of air through that.
Yeah.
Yeah, I think it's a dryer vent I just found it in the lab. And then this, of course, is leaf blower. So I get on here, and then Helena, if you want to turn it on.
Yeah.
So once we fire it up, the air coming out from the bottom of the disc raises me up, and I float on a cushion of air.
I can't control it!
Because the friction between the disc and the floor is so low, I end up floating wherever Helena and Russell push me.
I'm going towards the wall! It's like human air hockey! Okay. It's a bit unstable. Do you want to turn it off?
Wow, that worked amazing.
Not too much control, though.
I have no control whatsoever.
Yeah, no.
But this is great. So so we have the no friction down pat. I feel we need some way to actually move.
Well, something to push you along. I was thinking as you were going, like, you need like a broom or something.
A broom? Okay, yeah. What if we do like something low friction, like a broom, and something high friction, like that we could really sort of stick on the ground?
Yeah.
Works for me.
And then we could build two of them, and we would have two discs and two ways of moving them.
Are we gonna race?
And we can race! Yeah! Okay,
Yeah.
race. That's what we're gonna do. Here is an experiment you can do at home with friction. This is a toy boat. Yes, you guessed that right. And this is a wooden plank. Correct, that's 2 for 2. I put the boat on the ramp and watch what happens. Nothing! The reason why is because the friction between the boat and the ramp is enough to counteract the force of gravity trying to pull it down. But watch what happens if I raise the ramp to the right height, the boat slides down because the friction isn't enough and gravity pulls it down. But when we change surfaces to this carpet, let's see what happens. Same angle, I can raise it higher, 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 because there's more friction between the carpet and the boat than there was between the wood and the boat. Now, if you're thinking that we're just gonna do it with a small ramp, you're wrong. Because of course we're gonna max it out. Hey, Helena,
Hey.
This is amazing.
Thanks, I made it myself.
Wow,
Ready to climb it?
absolutely. Here we go.
Way to go.
Huh? No problem. So that was very easy.
Well, that's probably because the friction from your shoes is high enough so you don't slip.
Right, and the friction from my clothes is much lower, which is why I could slide down.
Right.
So how do we make it more difficult?
We'd probably have to make it higher.
All right, let's make it higher.
With the ramp at a steeper angle, I'll need more friction to climb up.
All right,
Ready?
I'm totally ready. Here I go. You try.
Okay, hold my drink. Here we go. Ooh.
Oh, so clearly we are not getting enough friction between our shoes and the ramp at this angle.
We should add some carpet, because carpet would add some more friction between our shoes and the ramp.
All right, let's add carpet. Sorry, here's your drill.
Thanks.
All right, carpet.
Yeah?
Same angle.
Yes.
And why have we done this?
More friction.
More friction. Let's give it a try.
Hey, way to go.
Totally able to climb the ramp. So, what do we do now to make it harder?
Make it higher.
Make it higher. Wow, it's really steep.
I don't think you're gonna make it.
Sure, if I take a really good run at it, I think I can do it.
I don't think so.
Well, there's one way to find out. No.
No.
Okay, so I can't do it. Is that it?
Well, how about Velcro?
Wow.
Right? It'll give you more friction, so you can try climbing with this. We'll give you Velcro knee pads, Velcro shoes.
Velcro. Velcro handholds, Velcro knee pad, Velcro on my shoes, helmet for safety, Velcro fill, Velcro dance. Okay, you ready?
Ready.
All right, here we go. Ha-ha, I did it! Creating friction between me and this ramp means I can stay up here for as long as I... No. No, Velcro. No. No.
Phil, you okay?
Velcro! Friction! Your turn.
No.
Our hover disc worked well. So well that we decided to build another. If we have 2 hover discs, then we can race them using different kinds of friction to push them along. Something that has low friction, like a dust mop, and something that has higher friction, like a pole with rubber balls at the end. Rubber has great friction. That's why we make car tires and the treads of our shoes out of rubber.
Okay, we have a giant race course that we've set up. We've got 2 low-friction hover discs, and I'm gonna use the low-friction dust mop version to propel my hover disc. And Helena, what do you have?
I have the high-friction rubber ball stick.
Start your engines! On your marks, get set, and go!
And we're off. Remember, Helena and I are using very different methods to get our hover discs moving. I'm using a low-friction dust mop, and Helena is using high-friction rubber balls. As you can see, my low-friction dust mop doesn't make enough friction with the ground for me to push myself. Helena, on the other hand, is having no problems.
Go ahead, you can beat him! He's way back! Before! He's way back for the win! It's Helena! She crosses the line!
Yes!
And here we have our winner. Yes, over the finish line. It feels way back over there.
Oh, man.
I'm still stuck at the second turn. Way to go, Helena.
Thank
Nice.
you.
So what was the strategy? How did it work?
Well, pretty much while I was using those red balls, I was getting friction, helping me steer.
You know what? I think we need a little bit more thrust. That would work even better if we had something pushing us even harder.
Definitely.
Wait, I have an idea. Wait, hold. I need your help. Come on.
Okay.
I'm at iFly Toronto indoor skydiving to talk to you about friction. That's Mike. He's gonna help me out. Okay, here we go.
Unfortunately, we can't hear what Phil is saying because there's too much wind. It looks like he's trying to tell us something about the friction. Yes, he's saying the friction from the air rushing up in the chamber is enough to counteract the force of gravity, which is why he's able to float or swim or whatever he's doing. Now it looks like he might be saying even something like air can have a lot of friction if it's going fast enough. And the air in this chamber is going fast, which is why we can't hear a word he's saying. Oh, well, he seems to be having fun. So how important is friction? Well, let's say I'm out for a drive. Car tires need friction to grip onto the road. Without it, my car wouldn't be able to turn at all. But that's nothing. Without friction, the bolts holding the wheels on the car wouldn't work. In fact, none of the bolts, screws, or glue on the car would work, and nothing would stop moving or stick to anything else. Even the trees would blow away with the slightest breeze. Friction is everywhere, and without it, nothing would work.
Okay, hover disc race round 2. This time we decided to have a little bit more thrust, so Helen and I are going to be using fire extinguishers. Now, do not use fire extinguishers at home. Fire extinguishers have a very important purpose, and it's not for this, but we've got these ones special. Are you ready, Helena?
Oh, yeah.
Oh, yeah. Okay, here we go. Russell?
So, racers, start your engines. And go!
Using fire extinguishers gives us a lot of thrust. But because the discs we're riding on don't have any friction, wherever we point ourselves, we just keep going in that direction, which makes steering very difficult. Cars grip onto the road and can go around corners thanks to the friction of their wheels. When you have no friction, it's kind of like moving on an ice rink.
Oh no! I'm out! Yeah! High five! Yeah! High five! Yeah! Okay, wait. Oh, I ran out of fire extinguisher at the end there, so I had to cheat a little bit. So 1 for you, 1 for me, and all of them for friction.
Or the lack of friction.
Or the lack of friction. Science Max, experiments at large. What do we do next? Larger fire extinguishers?
I think so.
Okay. See you next time. I know where we can get some, actually. We can go, if we go to the fire extinguisher store where we got these fire extinguishers, I think we can get like a...
Phil to Mission Control. Come in, Mission Control. This is Mission Control, Phil. We read you loud and clear. I would... Oh.
Greetings, Science! Greetings, Science Maximites! Welcome to Science Max Experiments at Large. My name is Phil McCordick, and today we're gonna be building an air-powered rocket. Too difficult, you say? Nonsense, it's easy. It's not like it's rocket science. Hey, it is rocket science. Cool! Here's what you need. You need a bottle and a cork. Make sure that the cork fits nicely into the bottle, and then you need an air pump, because you can't have an air-powered rocket without air. And on this air pump, you need a pin, the special kind that you use to inflate basketballs or volleyballs or stuff like that. Now, what you want to do is push the pin through the cork. You might want an adult's help for this. Push it through until it goes through on the other side, and then make sure you get a good seal with the bottle. Now you're ready to launch your rocket with air pressure. But first, let's do a few other things. Take your cork and put it in a tripod launcher. You can make this out of pencils or anything you want, as long as it stands up nice and solidly. And then, of course, you want to decorate your bottle so it looks like a rocket. This is my rocket. Pretty good, right? So stick the bottle on the cork like before, like that. And then you stick the pin in the bottom. And what we're gonna do is we're gonna inflate the bottle with air pressure, and then it's gonna launch. Okay, here we go. You know, rocketry really isn't something you should do indoors. Come on. Supposed to be a field. What's going? Why are there? Oh, it's in my shoe. Oh, this will do nicely. Now, don't forget to do this with an adult, and don't forget your safety glasses. Now set up the rocket in a nice big open area, and make sure it's pointed away from you. And then what you do is you pump the air pump. And it puts air into the rocket, which pushes down on the water, which will push down on the cork, until eventually... So be Science Maximites and come up with your own rocket design. Try different amounts of water, different fins, even a different size bottle. Try it for yourself and see if you can get one that goes higher than mine just did. How did I get in? I think it was this way.
Do you want step-by-step directions on how to build your own air-powered rocket? Well, don't worry. Everything you need is on our website.
All right, now it is time to max out our air-powered rocket. I've got Adam here. Hey, Adam.
Hey, Phil.
How you doing?
Good, how are you?
Good. Adam's from Logix Academy, and you guys go into schools and talk about science.
We do.
Fantastic. Do you guys do a air-powered rocket?
Yes, exactly.
Does it look like this one?
Looks exactly like that.
Oh, that's great. So how do we max this out?
So we want to add more pressure to this bottle to try to get it to launch a little bit higher.
More air.
More air.
Great, so what do we do?
So we're gonna use one of these.
Ooh.
It's the air compressor.
Right, which works a lot like the bike pump, right?
Yeah, exactly.
Cool.
So we're gonna have compressed air coming from here through this tube into underneath here.
Yeah.
And out that nozzle there, and you're going to put your bottle on top.
And out the nozzle
Just like
into
that.
the bottle, like that.
Yep, and now we want to be able to hold it in place. So we're gonna have these little fingers here that are actually gonna work to hold it until we want to let it go. So we're gonna lock it in place.
Oh yeah, look at that. Totally locked.
Exactly.
And then what? How do we launch
Now,
it?
you're gonna take this cord and go a safe distance away, and we are going to pull it.
And then we would pull it. Which one do you want to start with?
I think we should use this one here.
Okay, great. Now we put water in it, right?
Yep, you're gonna put water in there.
Why do we use water?
So the water is gonna act to push the rocket up into the air. The compressed air in here is gonna shoot the water out the back, and the water is gonna push on the rocket and make it launch. It's just to give it a little extra push.
How do I get it on there without spilling any water?
So just rest it next to the
Just go
launcher
fast?
there. Yeah, just go really fast.
Ooh.
There you go.
There we
A
go.
little bit.
Haha. And then
lock it in place.
Locking it in place. There's no air pressure in the hose yet, right?
Not yet, no.
First, we have to spool out the launch cord. So the air compressor has the compressed air in it. It's ready to go.
Yep, it's all ready to go. We just need to connect the hoses.
Adam, I've noticed it's snowing a little bit. Do you think that's any reason why we should stop?
I don't think so.
No, the science must go on. Blast shields down. Connecting hoses.
When we connect the air hose, the pressure from the compressor travels down the line and into the bottle. You can see the bubbles of air going in. Those bubbles are carrying more air into the bottle, giving it more pressure.
Here we go. 3, 2, 1. All right, there's the rocket. Let's do it again. Launching in 3, 2, 1. Woo! Nice. Success.
Success.
Nice. So, small bottle, worked really well. How do we make it bigger? I know, bigger nose cone?
I think a bigger bottle.
Oh, bigger bottle, yeah, of course, that's easy. How about this empty water bottle that we have now?
That might work, except that the top here is too big. I don't think it'll fit on our launcher.
Oh, yeah. So what should we use?
A 2-liter pop bottle might work a bit better because it'll be about the same size.
Oh, that's right. 2-liter pop bottles have the same opening as these small water bottles.
Exactly.
That's great. All right, let's make a couple rockets out of 2-liter pop bottles.
Awesome.
Pressure happens when you squeeze something or compress it. Solids do not compress very well. I will demonstrate. Solid? Is it compressing? No, okay. Liquids don't compress very well either. You can demonstrate this for yourself by getting a plastic water bottle and filling it right to the very top with water and putting on the cap and squeezing. You'll find that you can't really squeeze the bottle very much. But if you empty out half of the water, no, don't pour it on the floor, and then put the cap back on the bottle and try to squeeze it, you'll find that you can squeeze it a lot more. That's because gases compress much easier than solids or liquids. Here's what's going on. Say this container is, well, any container, and these magnets are air molecules. Now I'm gonna put the magnets in pole to pole so they repel each other and wanna stay a certain distance apart, just like air molecules do. There we go, a container at normal gas pressure. Now watch what happens when I add more gas molecules. they start to get squeezed together. And if I add more, the amount of space that each one gets is less and less. Now this container is under a lot of pressure. These molecules really want to escape through the top of the container, but they can't because I'm holding them down. If I took something like this plunger and I pushed them down even more, now they're really under pressure. They want to get out, but they can't because I'm holding them in. Now watch what happens when I let them go. They all pop out the top, and the container has returned to normal gas pressure. That's what happens when we put gas in a container like this one. These containers that hold compressed gas are made out of solid steel because you need something really strong or it might explode if you put too much gas pressure in it. That's why these are only filled up by professionals who know exactly how much pressure it can take. That is the power of pressure.
Our air-powered rocket was working pretty well, but there's always room to max it out. In order to do that, we need to understand how it works. First, we fill the bottle almost halfway with water, then we add air to the bottle. The air pressure builds up, and the air presses down on the water. The rocket takes off when we pull on the release valve, which was blocking the opening of the bottle. Once that happens, the air pushes out the water. It's the water that gives us our thrust, so the water is very important. Once all the water is gone, the air escapes and the bottle returns to normal air pressure. But by that time, it's high in the sky. Now the plan is to use 2-liter bottles instead of regular water bottles to see if they work better.
Now we've made a few more rockets out of 2-liter bottles, and I'm gonna fill this one up with water, and we're going to fire it again and see what happens. Now, the idea is that these will work better because they have more volume, and more volume means we could possibly put more air pressure in. It's hard to know until you try it, of course. But the other reason why it might work better is 2-liter bottles generally hold carbonated beverages, which means they already have to be made a little stronger than regular water bottles because they have to hold in the carbonation, which is just like air pressure. All right, ready to go. Okay, here we go. You ready, Adam?
Yep.
Okay, blast shield down. Pressurize! 3, 2, 1. Let's do another one. And 3, 2, 1. Whoa! Wow! This is the superhero design rocket, which I'm very excited about. All right, Adam, it's going really well, but before we fire this next one, how can we make it bigger, better, and more awesome?
Get more pressure.
More pressure. How do we do that?
Well, we're firing at about 90 PSI right now.
PSI, pounds per square inch of pressure, right?
Yep. So we could increase it.
We could increase it. So how, we're at 90 now, how high does the tank go?
Go to about 120.
120 PSI. Let's see what happens.
All right, let's do it.
Here we go. 90, 110, 120. Should we fire it?
Let's fire it.
Let's fire it. Here we go. 3, 2, 1. All right. Hey, actually, it worked okay. There's just a piece missing here, but I think the bottle is still okay.
Yeah.
So, 2-liter bottle, full pressure. I think we can still make something even better, even more maxed out. What if we used an even bigger bottle? You know the 5-liter ones that you see on a water cooler?
Yeah.
You think we can use one of those?
Definitely. I think we could use that. We need to change the mouthpiece size
yes.
to fit our launchers.
Well, let's do it.
Do it.
Help, I'm being crushed by all this pressure. A whole kilogram is being pushed down on every square centimeter of my body. 103 kilopascals. Actually, 1 kilogram for every square centimeter on your body is the exact kind of pressure that you and I are under at all times every day. We don't notice it because we're used to it, but it sounds like a lot, doesn't it? Well, it is. Here's an experiment you can do with a plastic bottle. Say at room temperature, there are 10 million air molecules in here. Doesn't really matter how many, but we'll say there's 10 million at normal room temperature. What happens if I heat up the air inside this bottle? This is warm water. What I'm trying to do is heat up the air inside the bottle because the air molecules, when they get hotter, move faster and need more room. So the 10 million air molecules are starting to escape out the mouth of the bottle and reducing the number of air molecules inside. And now I take the bottle out and cap it. Because the air molecules heated up and speeded up, they needed more room. Now there's less of them in the bottle. There's about 4 million air molecules inside this bottle, but they're all hot air molecules and they have a higher pressure, and you don't notice it because the air out here isn't crushing the bottle. But watch what happens if I cool the air inside the bottle. This is ice water. So what's happening now is the molecules are slowing down and they need less space. So they need less room and they're being crushed by the pressure on the outside of the bottle. Ha-ha! It has been crushed because the colder air molecules don't need the same kind of room as the hot air molecules. The room temperature air has crushed the bottle. The air inside has a lower pressure than the air outside. Pretty amazing. Even more amazing when we max it out. This is a steel drum. What we've done is we put some water in it and we're heating it up to boiling so there's nothing but hot air inside the drum. This is an airtight cap, which we use to seal the drum. And now we cool the drum off. Hey, Trevor, give me a hand. Ready? 1, 2, 3, you lift! That's good. This pool is filled with ice. What we're doing now is cooling off the steel drum, which will cool off the air inside it. Which means, eventually, the air inside the steel drum will be a much lower pressure than the air outside the steel drum.
Because this steel drum has a lot more volume than a 2-liter pop bottle, it takes a lot longer for the air to cool down. The other thing to think about is that it's a steel drum. I could stand on it and it wouldn't even dent. But sure enough, after a few minutes...
Whoa! Check it out! The barrel has totally crushed. The low pressure air inside the barrel wasn't enough to withstand the force of the regular air pressure that you and I walk through every day. The air pressure all around us is enough to crush a steel drum. How cool is that?
Our air-powered rockets have been working really well, but we still want to go further. Since the 2-liter bottle worked better than the water bottle, we think increasing the size again might make it more awesome. So now the plan is to switch our 2-liter bottle with a 20-liter water cooler jug and make a rocket out of that. Because the launcher nozzle, which holds the bottle in place till we're ready to launch it, isn't going to fit the opening of this bigger jug, we've decided to use the cap that came with the jug. If we screw the cap on, it'll work sort of like the cork. The air pressure will press down on the water and keep pushing against the cap until the cap has a catastrophic failure, which is a very cool way of saying that eventually the cap will break and the bottle will shoot into the sky.
20-liter water cooler jug filled with some water. This is the cap that'll work sort of like the cork. We put the air pressure in there, the cap can't take it anymore, pops off, and the thing flies, hopefully. Let's find out. Okay, that looks good. There. Let's do this. Go for pressure! Uh-oh. Uh-oh. Oh, no. Hilarious! That worked pretty well. It sort of does that. I wonder if it's aerodynamic.
No.
No. So, what else can we do to make it even more maxed out?
I think we've used the 2-liter bottles that work really well.
The 2-liter bottles are the best, right?
I think so.
So, what do we do?
I think we probably stack them. We stack them on top of each other.
Yeah.
That work.
I like that. So we put a whole bunch of them together.
Yeah.
Tell you what, I'll do you one better. Why don't we use 3 stacks?
Awesome.
We'll use 3 stacks, 3 launchers, 3 times the thrust, and we'll make a giant rocket out of 2-liter bottle.
Yeah, great idea.
High fives. Here we go. Gas molecules get further apart when you warm them up and closer together when you cool them down. So what happens if you keep cooling them down? Well, they turn into this. This is liquid nitrogen. Nitrogen makes up 78% of the air we breathe, but when you cool it down to minus 196 degrees Celsius, it turns into a liquid. It's boiling right now because at room temperature, nitrogen wants to be a gas. So the liquid nitrogen is turning into gaseous nitrogen, and all of the extra molecules are escaping through the top of the bottle. So what happens if I put a cap on the bottle? Right now, the liquid nitrogen is turning back into a gas, but because there's a cap on the bottle, the gas has nowhere to go. So the pressure is just gonna keep building and building until the plastic bottle can't contain it anymore, and it pops like a balloon. Science!
Our rockets have gone from small to bigger to even bigger. Now the plan is to use 3 2-liter bottles and create columns of them into a giant rocket. We pressurize them just like we did before, but with more thrust, it might work even better. Even if it doesn't work better, I'm pretty excited about this new plan.
Giant rocket! Giant rocket! You ready?
I'm ready.
Okay, blast shields down. Connecting hose. Dialing up pressure. Pressure is rising. It's bubbling. Bubbling. 100 PSI. Okay, stand by to fire. 3, 2, 1. Whoa! Woo! Awesome! Yeah, let's go check it out. Well, there you have it. Rocket Science Max. Experiments at large. Well done. Nicely, nicely done. Do you think we could fire it again? Yeah, it looks like it needs some repairs, though.